Thank you. All right, so, yes, thank you. So, yes, my name is Kamen Todorov. I come from Amsterdam, and I want to talk to you about how to pick the best vacation spot in the galaxy. This way. All right, so you've all seen the posters, and you got all the nice advertisement for the solar system. So there are all these planets that you can go to. But how do we know that it's really the best spot for you to go? How do you know how? So how do we know? Wait. How do we know what is what are the actual conditions on this on this planet? How do we know that it's actually as warm or as dense or whatever as you might think? Well, so that's what I want to talk to you. So first, we need to find the planet first before we can even consider going there. And how do we even know that there's a planet around this star that we've decided to look at? Well, the simplest thing that you could do is to look for these planets. Just point your telescope at them and at the star and see if there's a planet around it. This is a little bit harder than it seems because most planets are about as bright as a small candle right next to a lighthouse, and you're about 10 kilometers away. So it's not very simple, but we can do it. There is technology to do this. So you take a very big telescope, you do some tricks with optics, and you can nullify the light from the star, and what's left is just the light from the planet. We've done this several times, and if you do it, this is the same planet. This planet is called Beta Pictoris b. And if you do it several times over several years, you can actually see the planet moving compared to the star. So the star is like that little star symbol in the middle, but it's actually really, really bright. You wouldn't be able to see the planet if the light wasn't nullified. All right, so we've done it again for another system. It's called the HR8799 system. There are 3 planets that you can clearly see move very nicely, but actually 4 planets around this star. The 4th is in the upper left corner. All right, but what can we learn from these pictures? They're just pictures of a star and some planets moving or maybe not around it. Well, we can maybe learn the planet's length, the planet's year's length, so the period that the planet takes to revolve around the star. We can figure this out by just taking several images over the course of maybe decades. However, in some cases, the planets are so far away from the host stars that it would take centuries to be able to measure their period, even thousands of years. So we don't know this in all cases. But the other thing that we can really almost always measure for these objects is we can learn what's the temperature. So all of these objects that we've imaged so far are red hot, so they glow in the dark. They're so hot, thousands of degrees Celsius, usually 1.5 to 2,000 degrees Celsius. So they're very, very hot. Why can we only find those? Well, because they're hot, so they glow in the dark. We can see them. They stand out. They're also very big planets for the same reason. They're just so big and so bright that we can see them. And keep in mind, despite the fact that these are giant Jupiter-sized planets heated up to the temperature of red-hot iron, they are still about 1 million times fainter than the host star. So it's pretty tricky. Earth would be something like 10 billion times fainter than the sun if we looked at it this way. So, let's look for another way to search for planets. Yeah. So Alon already mentioned radio velocities and Doppler shifts to look for this. So what's going on here? Well, here's the idea. When I say that the planet orbits the star, that's not quite right. Technically, they're both, the star and the planet, are orbiting a common center of gravity. So as the planet orbits, the star wobbles. And then there's this thing called Doppler shift, or Doppler effect, or redshift, or something like this, that you may have heard of. Basically, the idea is that if something is coming towards you, you can see it a little bit turning a little bit bluer than it is. If something is moving away from you, you can see it go a little bit redder. And so we use this effect. We just stare at the star and see if the color changes very slightly back and forth between a little bit bluer and a little bit redder. And that indicates the presence of a planet around it. So this is how it works in practice. I'll just shut up for a second and let you look. So these lines are atomic lines. They come from the star. And what's going on is basically the star, the planet is moving the spectrum of the star a little bit to the blue and a little bit to the red, back and forth, very periodic motion. Okay, so what can we learn from this type of measurement? Well, one thing that we can learn is definitely the period of the planet. How long does the planet take to orbit around the star? Because we can see it go back and forth from blue to red very regularly. The other thing we can definitely measure is the mass of the planet. Why? Because we know what type of star it is, and we know how massive it is, and we know what type of mass is required to move it from red to blue and from blue to red, back and forth, a certain amount. The more you move it, the more massive it is. All right, so that's cool, but you need about something like 10 centimeters per second precision in velocity in order to find Earth around the Sun. That's very tricky. So maybe there's an easier way. And I would say that yes, there is an easier way. And this is sort of my area of study, and we call this transits. Basically, the idea is that sometimes we get lucky, and if you look at a star, sometimes the planet is oriented in just the right way that it regularly passes in front of the star. And so what you get, if you measure the brightness of the star, what you get very periodically is when the planet shows up in front of the face, you're measuring the brightness only, and you see a little bit of drop of brightness, and then as the planet gets out again, the brightness of the star recovers. And so you can learn quite a few things just from this measurement. It's very simple measurement. You can do it with a small telescope in your backyard if it's dark enough. And you can learn so much about this object. Yes, please. Again, you learn what's the period of the planet, so that's cool. But you also learn the planet size, because you know what type of star you're looking at, you know how big the star is. And then based on this drop of brightness, based on how deep this drop of brightness is, you know what fraction of the star is covered up by the planet. So you know how big the planet is compared to the star. Okay. Come on. All right. Yes. So, fine. But now we found a bunch of planets. Okay, Alona showed you how they're distributed in mass and radius. You know the mass and the radius by combining the transits and the radial velocity, so you can do both. You don't have to just do one of them, of course. But we want to study a bit about the atmosphere. So how do we do that? Well, so there are two things that you could do, and I'll focus more on one of them. But the first one is called secondary eclipse, and this is basically when the planet goes behind the star. So then you basically have the planet from the light from the planet itself obscured, and you can't see it anymore. And you can use this trick to estimate what is the light that comes from the planet itself. But I want to talk to you more about the primary eclipse, or the transit, which is basically what happens when the planet passes in front of the star. So this is sort of the geometry I want to talk about. So this is what's going on here. When the planet passes in front of the star, some of the light of the star passes through the atmosphere of the planet. And the atmosphere of the planet leaves an imprint on that light that has passed through it. And so here's the thing. Some species, some chemical species in an atmosphere will block light, but only in certain colors. Only certain types of light would be blocked, certain wavelengths. And so this is an example. So what's going on here is that the blue and the green are blocked by the planet's atmosphere. So the planet appears a little bit bigger in the blue and in the green. And so you can see that the transit depth is deeper. But the red, in the red, the planet is completely transparent. And so it looks a bit smaller, just in the red color. And so that means that the planet is, the transit depth is a bit shallower. And so if you measure the transit depth at several different colors, you can basically figure out a lot about what this atmosphere is made of. And so this is how it works in reality. So this is a paper by Heather Knudson on a planet called HG 209-458b. It's a very original name, I know. We're very proud of it. And so here's the idea. Basically, you're looking from the red to the blue. This is actually blue-violet that you could see. And the red is something that it's actually kind of more in the near-infrared. You can't really see this color. But they have measured basically the transit depth very accurately in all of these colors. And they have plotted what we call a spectrum. So on this axis, you see color. And on the y-axis, it's basically transit depth. And so what's going on here is that the planet looks a bit bigger in these wavelengths, in these colors, but a bit less big, like smaller in these wavelengths. So this means, so this is a serious, very strong indicator that the atmosphere of this planet, HG 209-458b, contains water. Water vapor in particular. So this is how we know that there is really a lot of water vapor on that planet. But this is a bit trickier, right? It's a little bit trickier because we also know or suspect that the atmosphere of this planet is very fluffy. So a lot of stellar light can pass through it. So this is this case here. But if it just so happened that the planet has a lot of gravity, it would sort of squish the atmosphere against it. And so even though there was a lot of water, you wouldn't see it because there's just not not enough light passes through this very squished, dense atmosphere. And there's also another option that could have happened, is if it was a fluffy atmosphere, but it had clouds. And then the clouds, they look flat, they look the same, they block all of the light, you can't see anything through them, so we would have thought that this is just a flat spectrum, we wouldn't have seen the water vapor. So this is sort of a challenge that we sort of have to deal with from time to time. All right, fine. So I've told you how you do all these things. But how do we figure out if this planet has a nice beach or something? Well, we first have to figure out, based on these studies that I told you, we basically will figure out what is the atmospheric composition. Well, this particular planet, has a lot of water vapor, true. It turns out it also has methane, carbon dioxide, and carbon monoxide. So all kinds of poisonous things. And this is not to mention the fact that it's about 1700 degrees Celsius. So it's a little bit on the hot side too. Maybe not the best place for you to visit, but this is sort of the general principle which we would use in order to figure out which planet you might want to visit and enjoy some time there. And so the other thing I want to say is that this is a very active area of research. We are working on this day in and day out. And we think we know a few things, so this is how we work, but of course everything is subject to change. Hopefully in a few years or a few decades, it's very hard to say, we will have a really good planet for you to enjoy a martini or a mojito with a nice umbrella. Yeah. So with this, I will just want to say one more thing. I forgot about this. So we are basically here. So this is basically a timeline of all the exoplanet missions that are important for us. And of course, the Hubble and the Spitzer telescopes have really helped. They have been amazing. I wrote my thesis using data from Spitzer. Of course, Kepler was dedicated entirely to exoplanets. And now, this year, we're about to launch TESS on the European side. So these are more American missions. On the European side, we have Corot and Gaia, which are going to be really amazing for exoplanets as well. We are launching Cheops very soon as well. And then James Webb and Plato and WFIRST and some others in the next decade or two are going to really transform this field and hopefully bring us to the point where we can see, we're fairly confident that there is something, that something can live on this planet. So with this, I want to thank you and ask if you have any questions.